Okay, no, the numbers are still increasing rapidly. Okay. Okay, I think let's wait a second that our speaker is back, and we can start. Okay, so good afternoon, everyone. Welcome to our NITheP colloquium this Monday afternoon. Thank you very much for joining us. And today we are very lucky to have Professor Amanda Weltman with us. And let me introduce her quickly to you. Amanda is currently a South African research chair in physical cosmology at the University of Cape Town. And she's at the same time a professor in the Department of Mathematics and Applied Mathematics at the University of Cape Town as well. Yeah. She also directs the High Energy Physics, Cosmology, and Astrophysics Theory Group at the same university. Yeah. Amanda did her PhD at the University of Columbia under the supervision of Professor Greene. After her PhD, I think over a little step back to South Africa, she spent some time as a postdoc at the University of Cambridge and came back to South Africa then around 2009, and has been based at UCT since then. Yeah. Amanda is well known for many contributions to, to cosmology that I won't list now, and she won also many awards that I also won't list, but they are published on the announcement of the talk, because otherwise my introduction will be very long. And we are very happy that today she agreed to give us a colloquium on fundamental physics in the radio sky. So Amanda, thank you very much for being with us today. And we are all looking forward to hear from you the latest from the big sky. You're welcome to share the screen.
So thank you very much, Francesco, for the excellent organization of these talks over the last few weeks, which I've watched a few, and they've been sort of quite encouraging to keep the brain working in different directions during this time. And especially for the invitation for me to talk. I think I'm the first in the series that's talking about really sort of useless stuff, the stuff that is completely theoretical and not necessarily applied to anything. And I think just to start, I wanted to take a moment to acknowledge. Can you hear me? Can you hear me?
Now I can hear you again. Yes, for a second you were gone, but I think now we can hear you again. Please.
Sorry, I think that is unfortunately the Internet of Things in South Africa. So I just wanted to take a moment to acknowledge the moment that we're in all over the world, and recognize that what a privilege it is to talk about physics and astronomy at a time when people are dealing with very, very real, everyday problems at an unprecedented scale, I think. So as you mentioned, I'm at the University of Cape Town, and I'm extremely grateful to the National Research Foundation and the Department of Science and Technology, or now Higher Education, Science and Technology, as they fund my research. So I'm going to do my best here to be fairly broad to a large extent, so that we all are on the same page, and your background in physics shouldn't matter too much. And I'll give some details for possible specialists and those who are interested. But to sort of start us off, I'm going to pose for you what I think are the interesting problems. What are the interesting problems in sort of physics and cosmology? I'll walk you through a big picture of cosmology with the connection to gravity as I'm going, and then look at the crisis that is possibly facing us as cosmologists, and finally come to the fantastic potential of radio astronomy to the rescue, so to speak. And I put the thank you here because, you know, I wanted to acknowledge what a privilege it is to get to talk about this sort of stuff at any time, but especially now. So what are the problems of interest? I've kind of broken them up into three classes. This is how I think. Others think differently. But for me, they're the very early universe problems, the problem of quantum gravity. Can we figure out a theory that allows for both a proper theory of gravity with quantum mechanics, quantum field theory, without problematic singularities, how the universe made its transition from a very early universe that was almost certainly some kind of quantum state to the classical universe that we observe now. Is inflation the correct theory? Can we sort of rule out all alternatives, or is perhaps there a better alternative out there that we're not seeing? And how did the universe begin? I mean, it's possible that there's no answer to this, even did the universe begin? But these are things that sort of interest me a lot about the early universe. And the late universe problems, I think I'll dwell on those a little more in this talk, which is trying to understand the nature of dark energy and dark matter, and the role that beyond the standard model physics can play in cosmology. Then there are a host of timeless questions, and I think these are the ones that are going to keep us going for quite a while. You know, the idea that we maybe have the wrong theory of gravity. Is general relativity correct? You know, there's a lot of talk in trying to go beyond general relativity, but we don't even fully understand general relativity. So there's a lot still to do there. And instead of trying to prove GR right, we really continuously try to prove it wrong and fail, which is comforting. The question of space-time dimensions, you know, do we live in 3+1 dimensions? And if that's the case, why? Sort of deep questions that we try to understand. Why do we appear to live in some kind of special place? Does physics force a kind of determinism on us? Is there a sense of free will, and what does consciousness mean? These are sort of well beyond the realm of this kind of talk, but I want to put them in there because they're things that when you start to think about questions outside of the bounds of time, you can't help but go there. And finally, the millions of fantastic, exciting, interesting puzzles in astrophysics, and what else we can learn about our universe by studying these sort of niche problems, which is actually where I'm going to go eventually today. So those are my sort of list of things that are interesting to me right now. So let me start by explaining to you how we build a theory. To have a good theory of the universe, we need to sort of have four things. One of them is our theory of gravity, and our best candidate right now is Einstein's general theory of relativity. The other is a theory of matter and its non-gravitational interaction, so the standard model. So that t-shirt over there, some of it might be familiar to some of you. It's ICTP's t-shirt for kids. It's great. It's got the Einstein-Hilbert action and the action for the standard model on there, including the Higgs. So I put that up there instead of putting up the equations. So those are the two sort of things you need to figure out are your theories. The choice of symmetries, meaning some kind of geometry of the universe, and the choice of topology are not, they're things that are imposed upon you by the data. Of course, your theories also have to match the data, but the theory doesn't fix for you your geometry or your topology. Einstein GR plus a standard model can work perfectly well in different topologies, not all, but different. I included this fun picture because it feels like 2020 is a bit of a Klein bottle, going round and round in circles and, you know, going inside ourselves in ways unexpected. But those are sort of the ingredients that we have. So two pieces of theory that we build ourselves, and two choices that we have to make based on observational data, of course. Everything needs to be observationally sound. And just those together, I call these the known knowns, right? The reference is maybe familiar to many of you, maybe not. These elements alone give you the conclusion that the universe began in a hot, dense state that has expanded into what we see as the CMB today, right? The cosmic microwave background radiation. We know that 13 billion years ago, the universe was, you know, very, very small, and it's expanded to what we see now. And I've got there the sort of progression just from COBE to WMAP, which shows you sort of how far we've come in being able to see the small fluctuations in the temperature in the sky. So that is a map of the CMB. The first one is you can just see the granular levels, right? And the dipole anisotropy. And the second one is because the solar system is moving, and that large red plane. And the third one that we generally try to remove is because of the motion of the galactic plane. So it's sort of really dramatic observational confirmation that our theories are at least going in the right direction. So what we're looking at there, you know, I include this for non-experts. For those of you who are expert, you know, maybe it's a nice thing to show your kids. But when you're looking out, when you look up into the sky, you can't see past the clouds at some point because light scatters off of them. And when we're looking back at the CMB, that's what we're looking at. We're looking at the last surface from which light could scatter. So the CMB is not the very beginning of the universe. It's quite a bit after the Big Bang even, but that's what we're seeing. And to figure out the physics of what happened before requires different tools, right? The CMB is not the only tool at our disposal. So to give you just a little bit of a glimpse of what we have here, I can zoom in on a cold spot, just like you learn in school, right? Blue is cold and red is hot. You can tell who's homeschooling their kids in this pandemic. You zoom in on the cold spot, and you can see here that in the very, very early universe, there were tiny overdensities in matter that clustered, formed stars. Stars start to switch on. The stars attract to each other and eventually form galaxies, and the galaxies cluster as they do, as matter attracts matter, and they form this beautiful web in the sky. Galaxies become clusters and superclusters, and eventually you get this cosmic web spread across the sky, and that's the slice from that tiny little bit of the blue spot, the blue cold spot, seen by WMAP. So it's a very nice sort of simulation to give you a sense of what you're looking at and where it comes from. Sort of something that I'm going to touch on again later is geometry, which I think is quite important. And so how do we understand what the geometry of the universe, i.e. is the universe closed? Is it flat? Is it open? And how do we figure that out? So there are a few different tools we can use, but one of them is also from the CMB, just looking at characteristics, spot sizes. So looking at the size of the cold versus hot spots. You can imagine if you're sitting at this telescope and you draw lines on which those photons are moving. If your universe is flat, they move on different lines to if it's closed on the right-hand side or open on the left-hand side. And so the characteristic spot size is different depending on your geometry. And so you can learn about the sort of curvature of the universe in that way. There are other ways, but this is one of the ways that we learn about it. So we learn a lot from the CMB. It's not just the temperature that gives us information, it's all kinds of other things as well. And this is a sort of lovely image that I really enjoy because it shows how much happened between sort of the very beginning and that the CMB, and then the stage that we're in now. The sort of curve up is the accelerated expansion of the universe that we're experiencing now, which I'm going to talk a bit more about. So there's sort of two pictures of the way that I think about physics and the universe. The one is this cosmology, which is the sort of big picture, and the other is particle physics, which, you know, is this really organized table of allowed particles. And the table of allowed particles is actually a very small wedge in the parts of the universe that we understand in cosmology. The remaining stuff, the so-called unknown knowns that I'll talk about in a moment, are really dark. They do not interact electromagnetically, and so we don't actually see them. So here's the sort of kid-friendly version of that, which is all the particle plushies, which one day I hope somebody will buy me. You can see that the Higgs boson was theoretical at the time. It's obviously not anymore. I don't know why dark energy doesn't get its own plushie, but there you are. So the known unknowns that I referred to, this is the dark universe, right? It's dark matter and dark energy. And just to walk you through, dark matter, essentially it's matter stuff, so it behaves in a matter-like way, interacts gravitationally, probably weakly, but it does not interact electromagnetically. So it doesn't interact with light. So we don't see light scattering off these particles, so to speak. We infer its existence from its gravitational effects on the light that we do see. So the simplest intuitive explanation is that we can weigh a galaxy by looking at the speed of the stars moving around that galaxy. And so if we considered, you know, even our own sun, and we look at the velocity of the Earth moving around the sun, we can figure out the mass of the sun. And so, you know, if the sun were much heavier, we would have to move faster to stay on the same orbit, right? If we moved any slower, we would be on a closer orbit, and if we moved much faster, then we would be we'd be further out. So so essentially, understanding the velocity of stars around a galaxy at the edges of a galaxy allow us to weigh the galaxy. And so we can do this, right? We can weigh a whole bunch of galaxies, and we write down the theory, and we look at the observation, and they're just very, very far apart, right? The observation is those data points, and the predicted theory is the sort of curve. I don't have a cursor on here, I'm sorry. It's the curve that dips up and down. It looks like South Africa's COVID curve right now, right? And so the prediction just doesn't match the data. And the simplest way to make it match is just to put more matter stuff that is not experiencing for, electromagnetic interaction. And so that's sort of a very compelling case for dark matter. There are actually several others. Dark matter also lenses objects. It causes lensing as the light moves past. So lensing, if you've never heard of it, or you don't know much about it, it's basically the fact that light in general relativity, light moves on straight lines relative to your curved space. And so if you have a very heavy object, the light sort of bends around that heavy object, and dark matter will change in very subtle ways the way that lensing works. And so you can look at all kinds of gorgeous lensing images and get information about dark matter. So there's a whole bunch of other observations that give us little bits of hints. So we only see really indirect evidence of dark matter. There's no direct detection. There've been a lot of lab experiments, and none of them have really panned out, which is quite interesting. We know that it's probably cold, because if it were hot, it would change the early universe. So we understand a little bit about dark matter, but there's a lot that we still don't understand, and there's a lot that we can still do. And South Africa is expected to make real impact here with MEERKAT and the SKA as well. Even less well known than dark matter is dark energy. It's the most poorly understood. These little screenshots over here are from NIThePhysics, which is just a fantastic YouTube channel. And I've put the link at the bottom there so that when you're looking at the video later, if you want, you can click on the link and watch the video. But I found this the nicest way to explain dark energy. Sometimes that's just the way it is. And so essentially what you've got here is that we're standing on our own planet. When we look out at distant galaxies, they're moving away from us. Okay, that's fine. But not just are they moving away from us, they're moving away from each other, and they're moving away from us and each other faster with time. And so it appears as though there's this accelerated expansion in the universe. Now, gravity makes things cluster, right? You wouldn't expect that. You wouldn't expect the universe to be accelerating in its expansion. It's like having a fundamental particle that has intrinsic negative pressure. It's just intuitively not obvious that such a thing can be. And so dark energy poses a lot of problems for understanding the universe, and it makes up a large part of the energy budget of the universe. So why do we even believe it exists? Again, there's a host of observational hints. They started off quite early, right in the 1980s, but I think still in the 90s, people were talking about acceleration with the opposite sign. They were expecting the universe to decelerate. So the hints were not necessarily listened to until type 1a supernova were really well studied. And the realization was these guys make really excellent standard candles, meaning standard measures of light, and they could allow us to measure distances and figure out the evolution of the universe, and the fact that it appears to be accelerating in recent times. And so this was a really big result. The WMAP gives us a flat universe with 23% dark matter, 5% regular matter, all the rest is dark energy. But the Supernova Cosmology Project, all of these different projects bring together the same idea that basically there's the sweet spot that we happen to live in, where the bulk of the universe is dark energy. And the Nobel Prize was awarded for this, for the observation of dark energy, which is quite unusual because it's a truly unknown, it was the observation of acceleration. I think dark energy is maybe too much to even claim. So, again, the things we understand about dark energy is only its effects on the universe. We don't fully understand what it could possibly be. And we have some ideas, we have theories that could explain it, but that require us to either modify the way we think about cosmology or to modify the way we think about physics. So we either need a change in, if you remember the first slide where I had gravity, particle physics, and then geometry and topology, it either requires a change in the way we think about gravity or a change in the way we think about particle physics. Those are sort of the only two options that we have at the moment. And there are a host of sort of interesting theories and possible observations you can do. And again, South Africa has a lot of impact here, and the SKA will have a lot of impact without a doubt. HIRAX will as well. And on the theory side, we have people, I'm included in that, working on these things as well. So there's a lot to learn about dark energy. So overall, when it comes to the known unknowns, dark matter, dark energy, they're inferred from indirect detection. There is no direct detection. We've tried lab experiments for dark energy. We've tried lab experiments for dark matter. We haven't seen any of them in any direct way. And each of them requires some kind of new physics. So, it's the tiniest interlude to talk about Urbain Le Verrier. If you have not heard of him, he is the man who discovered a planet with a point of his pen. And today is a good day to talk about the solar system and planets, because I think it's the 14th anniversary of Pluto being downgraded from a planet to a dwarf planet. I refuse to acknowledge that. And when I teach my kids about the solar system, Pluto is in there. And so, what happened with Urbain Le Verrier is it was understood that Uranus, the motion of Uranus was not understood. So it was understood that something was wrong with the motion of Uranus. And no one could really figure out why. It turns out Uranus is an oddish planet with a tilt in a strange direction. But beyond that, it wasn't clear. If you put together the trajectories of all the other planets so far, it wasn't clear why Uranus had this wobble and didn't fit the trajectory that was predicted. In those days, these celestial mechanics calculations were an ordeal. And Urbain Le Verrier said, what if there's another planet on the outside of Uranus causing this unexpected motion? And sent his results to the Berlin Observatory, and they looked for them the very day that they got the results. They looked and they found Neptune. And so Neptune was really discovered in this theoretical way by him. And that's very much one mode of doing physics, right? We look and we say, something's wrong with our theory. There's this bit of data that doesn't match all the theories we have. And so there must be another particle out there, right? If you think about the Eightfold Way, the history of particle physics, every time something didn't quite match, a little bit of missing matter, we proposed the neutrino. And then we find those particles. The neutrino was there. All of these particles have existed that we've looked for in that way. And so that's one approach, is to say, well, dark matter is a new particle. Dark energy is a new particle. That's entirely possible. A new planet way of doing physics. But, fast forward a little bit, Urbain Le Verrier was also working on the problem of the precession of the perihelion of Mercury, which also didn't fit with observations. And he said, well, this Neptune thing worked out pretty well. I'm going to propose that there's a planet between Mercury and the sun. I'm going to call it Vulcan. And that's the planet that is, has messed with the motion of Mercury. That's why Mercury's motion doesn't quite work. And there, the new particle thing didn't work, right? It took another 50 years for Einstein to come along and say, actually, our theory is wrong. We can't be using Newtonian mechanics to do celestial mechanics. We need a different theory. General relativity is the right theory. And he explained why the Mercury's motion was not as had been predicted. And there's no Vulcan, right? Not that we know of. So that's really the alternative. It's possible that dark matter and dark energy are not new particles, or one of them is not a new particle. It's just that we've got the wrong theory. And it's always easier to propose new particles, I think, than to revolutionize our theories. But I always feel like the story's worth telling, because there really are only so far two real ways to do things, at least in this cosmology, particle astrophysics world. And those are this kind of two big options that we have. And that's really, if you want to write down all the solutions to dark matter and dark energy, they fall into one of those two classes. So those are our known unknowns. Coming back to cosmology, our parameters are, really precise. We've got each of the parameters that describe some component. The baryons, the cosmological constant is the quantification of dark energy, the total neutrino density, etc. Every parameter is really well measured, and each experiment is getting more and more precise. I've got Kobe on the left. It looks so fuzzy now. Even WMAP looks unimpressive relative to Planck. And that's only Planck 2013. The data just gets better and better. So it feels like we're moving towards this consensus, this precision state of cosmology. Cosmology went from a field that was philosophy, looking out into the sky and having ideas, to precision. And we thought that things would move in that direction indefinitely. I certainly did 10 years ago, maybe even 2 years ago. And now we seem to have reached a stage where I think that's no longer the case. I think we're reaching a crisis, which is good. Crisis is always good. It gives you a chance to have a healthy revolution. And there are a bunch of possible crises. So dark energy and dark matter are not resolved, right? We don't have any theoretical candidate for inflation. There's a lot of work still to be done. Remarkably, we don't fully understand galaxy formation. There's missing baryons, which I'll explain a little bit later. And sort of what I focus on this slide is the H-naught tension. So this is the tension and what the Hubble constant is. So if you look at the bottom image, you can see that, 20 years ago, the value was somewhere, all experiments had the value somewhere between 65 and 80, right? And that's the value that actually came from Cepheids, and slowly the error bars have gotten smaller and smaller. And I remember, when I first started working in cosmology, I think the conversation was that it was between 50 and 100, and there was a lot of laughter. It was like 50 plus or minus 50, or 75 plus or minus 50. So it was a very big range that H naught could be. And as these experiments have happened, this, CMB and Cepheids have perhaps the most diverged. There's other papers that give different values. I've just picked this image because it's so nice and clean. As the precision has improved, the crisis has become apparent because the error bars no longer include each other. So that's a crisis. That's something to think about. Something's wrong in somewhere, in the theory, in the data, something is wrong. And so, you always got to take an opportunity and look at what you can do. And I've thought about this quite a bit, and I think there are possibly 4 roads to understanding and improving on this problem. The one is looking at existing data, methods, analysis, how that was all done. It is well outside of my my work. I don't work on that, but there are excellent people who do, and there's a lot of really interesting talks that you can now find on YouTube even, to learn about the different techniques that people are taking. The next is to consider possible new physics, and this is something that, Julian Lorena, who's a colleague at UCT and one of our joint students, have been looking at for the last while. It's not an easy problem, but, it could be that new physics explains why it is that different distance measures, large-scale observations versus small-scale observations, long-time observations versus recent ones, give you a different result for H naught. So that's a possibility. A third possibility is that our theory of gravity is wrong. Possibly we need a new theory of gravity. And the best, testing a new theory of gravity with cosmology is not really going to help us, because our observations are really built on the priors of our gravity theory. But we could use gravitational waves as a testing ground for a new theory and then feed those results back into cosmology. And this is work that my student Irvin Martinez is doing. He's doing a fantastic job there, building a set of simulations basically for us to look at gravity as an effective field theory and treat astrophysics in the same way that you would treat sort of quantum mechanics, quantum field theory. And so then we may have progress that way. Another option is to consider new probes of distance of cosmology to resolve that tension. And this isn't how I landed up working on fast radio bursts. It was a completely different direction, but I've realized that may be one direction. And so this is work that Anthony Walters, who was my PhD student, and is now a postdoc, and Emma Platz, who's my current PhD student, have been working on with me over the years. And really, there are a bunch of different things you can do. So I've just picked 2 papers here that have looked at this particular point, that have looked at the fact that you could use fast radio bursts to constrain H naught in various ways. And so sort of the idea is that there are a lot of different approaches here, and I'm going to talk for the rest of my time about the possibilities with radio astronomy. So I've titled the slide "Radio to the Rescue" because I think radio astronomy is a fantastic window of opportunity for us in South Africa especially, but in Africa more broadly and also around the world. So as a brief sort of introduction, the idea that there were radio waves coming at us from astrophysical sources was discovered by Jansky in the typical astro way, trying to get rid of noise to improve a very practical, simple thing. He wanted to improve telephone reception for Bell Labs. He discovered that there were radio waves in all directions coming at Earth. They're extremely weak. If we remove the solar ones, all the radio waves except for the solar ones wouldn't melt a snowflake. So they're relatively weak. They're low frequency, long wavelength, and they fill up this wide band from sort of, around 10 megahertz to a terahertz. So they take a big chunk of the observing band, so to speak. The large wavelengths are very good because that means that we can actually see them with the ground-based experiments. And we can also probe the hyperfine splitting, look at the 21 centimeter hydrogen line, basically using radio astronomy because that's where it lands up in the spectrum. And so we have a lot of potential with radio telescopes because we can build them on the ground. the atmosphere absorbs infrared, UV, X-ray, and gamma ray. And so those telescopes need to be launched into space. It just makes them far more expensive and complicated to manage. And radio and optical are the sort of rare windows of opportunity that allow for ground-based astronomy. Discoveries in the radio are actually, plentiful. I was delighted to learn this myself. And the question really is, what's next? And can we be in this next revolution for radio astronomy? And so, there are a lot of things that you can do with radio astronomy. There are a lot of things South Africa is doing in particular. To me, perhaps one of the most exciting is the discovery of fast radio bursts. So these are transients. They were discovered in 2007. There were only a few of them up until last year. And between last year and now, there's several hundred. So, and there will be thousands observed in the coming years. So that's a field that's really burgeoning and very, very exciting. The progenitor mechanism is currently unknown. There were very few hints. In the last few months, the hints have become very strong. So the field has changed very dramatically. And the number of classes are unknown, just like gamma ray bursts and supernovae have different classes. It's possible that fast radio bursts do as well. They're bright, so that's Jansky, and they're brief, so that's millisecond scale. So there's great possibility for science and discovery. If you care about the theories, a group of us put together this beautiful catalog. The webpage is there to see the wiki, which has all the theories and ways to rule them out. But there's also a publication that you can find on the archive or physics reports. I've also looked at various other things you can do with FRBs, and I'll talk a little bit about some of that now. But there's really great potential here, and I think that's sort of worth paying attention to. So the first, I tried to catalog what we know. And this changes very fast, right? A lot of these lines I added after attending the last conference I attended in person, which was in February, was an FRB conference at the Flatiron Institute. And a lot has changed since then. So we know their millisecond duration. The frequency range is so far quite broad, and it keeps getting broader. They've been seen down to 300 megahertz. There might even be a 200 megahertz one that I haven't included here, and all the way up to 8 gigahertz. So they're in a biggish band within the radio. We've localized some of them to hosts, not all of them. So by hosts, I mean galaxies. So you see which galaxy they're coming from. Only a fraction of the parameter space is observed. We can estimate how many we expect to see, and there should be probably tens of thousands a day. And obviously, we're not yet seeing all of them. Some of them seem to repeat. Some of the ones that repeat seem to have periodic repetitions. Some do not. So coming up with physics mechanisms that can explain all of these features is quite an interesting puzzle. And so they're very, very interesting. They are, at the very least, most of them are extragalactic, meaning outside of our galaxy. And we see them out to at least low cosmological redshifts, but there's nothing to say they don't go much further back. It's just that it's very hard to see them further out. They're excellent traces of their source environment, and I'll explain that a little further later on. Some of them are polarized, some appear to be linear, some appear to be circular, but it's entirely possible that they're picking up that polarization from the magnetic field that they're propagating through between the source and us. So it can be very hard to detangle the effects of the intergalactic medium and the host and what is intrinsic. But that's the sort of interesting part. And the sort of a key descriptor is the dispersion measure, which I'll describe in a moment. And there are a lot of uncertainties in the dispersion measure because it's hard to break apart what came from the host and what came from the intergalactic medium. We don't know how far out they go in redshift. There are lots of theories. And possibly the most compelling right now is magnetars for a number of reasons. So the dispersion measure is as follows. Essentially, you have this brief pulse that arrives in the radio. Now, because this photon is traveling through the cold plasma between the source and us, there's a delay in the arrival time of different components that is frequency dependent. And that delay is a function of the frequency. So it's 1 over frequency squared. And so the dispersion measure is a way of us, it gives you a probe on the number of electrons between us and the object. If you have a very high dispersion, so it's spread out quite a lot, you know the object is coming from the light is coming from very far away, and it's gone through a large number of electrons. And so we can learn about the source and about the environment in between by studying this dispersion measure. And we realize at the outset that they're extragalactic because many of them have large dispersion measures and appear to be within host galaxies now. So, you know, I asked with my student Tony and my student at the time, Amadeus Witzerman, we asked the question of, could you, and to faculty, Brian Gainsland and Yin Jamar, but of course I'm going to focus on the fantastic student work here. We asked sort of strange question, could you constrain curvature? And I'll explain in a moment why I think curvature is still important, but we said, you know, can you constrain curvature using FRBs, right? There's a claim that you can get constraints on dark energy, but what about curvature? And so we looked at this, and the question is, where does cosmology fit in, right? So this is a slightly more technical slide, but you can see that essentially in that E of Z, you've got cosmological parameters. Omega matter is the density of matter, omega dark energy is the density of dark energy, and omega curvature is the density due to curvature. Z there is the redshift, so it tells you how far out you are. And so essentially the cosmology that is your universe is encoded within that averaged out dispersion measure. And so we can, you know, begin to probe and see if it's possible to get cosmology constraints. So this is a slide taken straight from Tony, from one of Tony's slides. And so essentially what you've got is you want to figure out the IGM component. That's where all the cosmological information is. We need to subtract off the Milky Way contribution to the dispersion measure, which we can do. It's an astronomy problem. And we want to subtract off the dispersion measure from the host galaxy. And that's the hard part. So if there are ways around it, but that's the hard part because that's the big unknown, right? But the cosmological information is in that middle bit. So what Tony did is he simulated an FRB catalog. We used Hyrax as a fiducial kind of experiment, but the results would be similar with other experiments. And he considered a modest 1,000 FRBs between us and a redshift of 3. And with his forecasting, you can see that, you know, combining the CMB with baryon acoustic oscillations, supernovae, and H0, you can't do very much. The FRBs themselves don't constrain you very much. Your biggest constraint is over omega baryon, which is not surprising, right? Because omega baryon is telling you about the number of electrons between us and the FRB. And so that's no surprise that you're getting constraints over on that parameter, the parameter that quantifies that. Looking at curvature, it's unconstrained by FRBs alone, but again, putting in all of the priors, you can get some improved omega baryon relative to omega curvature constraints, obviously if you allow for that freedom. And so we sort of thought that was very interesting, but of course, as people relatively new to radio astronomy, we input some priors. So one of those was that FIGM is a known quantity. So we input the if I just go back here, you can see FIGM over there. It's the baryon mass fraction. So it's the fraction of the intergalactic medium that is essentially baryons. And so we just thought that was a known thing, and so we looked up that number and input it. But it turns out, of course, that that's actually not that well known, right? We think we know what it should be, but it's not that well known. In part because what I said to you before about the fact that only 5% of the universe is baryons, it's even worse than that. We only see 5% of that 5% from the BBM. We're only able to constrain a small percentage. The rest, we only see 70% of them, 70% of that 5%. The rest are missing, right? The 30% remaining are just missing. They're expected to be in the warm, hot intergalactic medium, but it's very difficult to actually observe them and get better constraints on them. And so, you know, Tony realized that if we allow FIGM to be a free parameter and take cosmology as a fixed prior, we could then get, you know, take omega baryon and omega curvature fixed from cosmology experiments. We could then solve the missing baryon problem by putting a constraint on FIGM. So if we can get FIGM down to be the right value, that would basically tell you where the missing baryons are. Why? Because these photons are probing the baryons between the source and us. And this is a sort of very nice paper. And, you know, as a theorist, you write papers and then they get ignored, or nothing happens for 5 years or a few years, I don't know. But FRBs move extremely fast, the field. And within a couple of, within a few months of that paper, this was observationally proved, right? So basically what J.P. McCart and colleagues did is they looked at localized galaxies. I think there were actually 5 of them. I've got 4 of them here. I think they used a 5th one, not from ASCAP, but they put together ASCAP and VLT observations, and they showed that missing matter, and they only needed very few FRBs, right? That's what's so remarkable. So here you've got an FRB, it's just left the edge of its galaxy. You can see the light is moving towards us. Here we are on Earth. And if I zoom in on it, I can break it up into frequency components, right? The colors there are just to tell you that it's, you know, the frequency. And if you're going through empty space, they all got the same speed. But if you're going through stuff, baryons, then they're slowed down, as I explained to you, about different rates. And because these FRBs were localized, because we knew the exact location and they were on the edge of their galaxies, they could do this. So this is a really remarkable thing where the theory and the data were just, you know, very close together. And the missing baryon problem, I think, is solved. I think that's solved. So there's a host of other really interesting things you can do with FRBs. And this is not all the papers on the field, of course. I've just summarized some of them because I think that's really interesting to realize. And I gave a talk this week. There's a cosmology from home workshop. If you're not registered, you might want to try still register, though it may be full. But there was a pre-workshop a few months ago, and I gave it a plenary talk at that pre-workshop. And based on that talk, you know, a bunch of the guys who were in the audience said, actually, I think we can write a new paper on this. And they put out this paper on non-Gaussianities, which I you know, give mention to here. So it's a really rapidly evolving field, and one that you can make major progress in, I think, if you're willing to think hard about astrophysics and cosmology at the same time. So in terms of the early universe, because they probe the electron density along the path that they're moving on, they'd be sensitive to helium reionization. To do this, though, requires priors. In every single paper I'm telling you, you need to bear in mind that they're big assumptions. So here they need FRBs all the way out to redshift of 5, which is, you know, possibly ridiculous and impossible. There's a whole lot of dark energy, late universe constraints that you can get, dark matter constraints that you can get from lensing and even micro lensing, okay? If there are machos out there, then FRBs that pass by the machos would be micro lensed, and you should get a double peak in your FRB. Now, at first, it just looked like FRBs were single signals, but looking at them, they may have substructure. In fact, they do. We just don't understand it fully yet. And so there's a chance to really probe like fundamental physics issues by using FRB light as tools, as measures, you know, your rulers in some sense, your candles. So there's a huge amount of potential here. Likewise, we can learn about we can learn about the intergalactic magnetic fields and distinguish between astrophysical sources and primordial sources by studying fast radio bursts and breaking apart the dispersion measure and the rotation measure and understanding what's actually going on there. Again, there are always assumptions. This one is, of course, that it's a neutron star. Otherwise, you don't know anything about the magnetic field. There's broad cosmological implications as well on different scales. There's implications for truly fundamental physics. Like, does the photon have mass, right? If the photon has mass, then there would be a time delay to photons coming at us from FRBs, and that time delay would go like 1/nu², right? The same thing that electrons do, the same delay that electrons cause. And so you would need to know the redshift and remove other uncertainties, but you can get spectacular constraints on the mass of the photon because of these effects. Really a lot of physics waiting to be done by understanding fast radio bursts. So I wanted to really bring that to people's attention, and I think there's a lot to do, but you have to be very, very careful about your priors. And then, you know, radio astronomy brings us a lot of interesting ideas. So I've just got here about the 4 localized bursts. Sorry, there's a point that I personally found very interesting, which is that they all appear to be at the edge of their host galaxies. So you might, I don't know what your prior is, right? if I said to you that they're in hosts, your prior might have been that they're spread across the host like butter on toast. And this makes it look like they're actually sitting at the crust on the toast. They're not spread evenly like butter. But it's also possible that they're just more easy to see when they're at the edge, because they don't have to go through the whole galaxy. So it may be that we've got a bias in there. It's not clear. But whatever the case is, we learn a fortune about them by getting a handle on where they are and localizing them. So radio astronomy brings with it other riches. One of them is the possibility to do intensity mapping. I think there's no better, I like the analogy of looking at pointillist art, where if I zoom out, I can see very well the Sunday on Le Grand Jacques Bassura, and I can see what's going on there, the dogs playing and the children picnicking, and etc. You didn't need to do a perfect painting for me to recognize the story going on there. But if you zoom in, you realize that nothing has been painted correctly. They're just dots. And it's unresolved dots that when put together, the eye figures out how to map. And in some sense, that's what intensity mapping is doing. We produce maps of large scale structure without actually zooming in on any one galaxy. And so it's a kind of it's a useful tool to give you the broad, big picture without being too intensive in any one thing. And it's in some sense, it's a much harder science to do than fast radio bursts. So I promised to come back to curvature. And the way that I got to thinking about these things was actually George Ellis asked me if the SKA could rule out the multiverse in any way. And so I thought, well, what are the different signatures of the multiverse? And one of them is curvature. And if you measure different measures of curvature, you rule out different classes of the multiverse. And so I thought, well, okay, let's see if the SKA can constrain curvature. That would, or observe curvature. And it turned out we don't even need to wait for the SKA. Hyrax could do this. And what you need to do is break the degeneracy between dark energy and curvature. And there's a very nice paper that I wrote with, the very hard work was done by Amadeus Witzerman, but the intellectual, this was work done with Chris Clarkson and Mario Santos as well. Of course, Mario taught us how to do all of these things. So the idea is that if you can map out if you can map out a large cosmological volume of these galaxies, you don't need to actually have a good resolution of them. And because they trace the matter, you get intensity maps of matter essentially by doing this. And you can go to far higher redshift than with optical galaxies. So we had, with the optical galaxy survey. So we had two possibilities to do this. The one, we want to get rid of the role of dark energy, right? Because dark energy and curvature, you can see they could get in each other's way. So the one is to just go to high enough to high enough redshift. So you assume a constant equation of state, you skip the dark energy dominated region. If you look at redshift 3, 4 above, dark energy should be playing no role, then you're just studying curvature. The other is to consider some evolving dark energy and then allow for curvature as well, essentially. And then you use the MCMC to constrain your curvature. And, we used a Hyrax-like survey. So again, this could be done for any intensity mapping experiment. You can see papers there. Marta Spinelli was also co-author. And the possible constraints that we could get are much stronger than Planck or any existing experiment. You can see by an order of magnitude better than Planck. And we can also study evolving equation of state, which Planck itself doesn't do. And so that's a very nice sort of result. And it's a proof of principle for what these experiments can do. Just to introduce you to Hyrax briefly, Hyrax is both an intensity mapping and a fast radio burst machine. So it's designed to both see transients and also have this long time observing to build up beautiful cosmology data, and will not just probe curvature, which is just my hobby horse, frankly, but also allow us to probe dark energy. And with cross-correlation with other cosmological surveys, hopefully get, the world's best constraints on cosmology when the time comes. At the bottom left there, I've got one of the master's graduations, I think, Kavi, Cynthia, John Sievers in the back there, and a bunch of students. On the right, one of the students putting together the dish. And the middle is, of course, the artist's rendition. So just to explain the name, this is the 7, you may only see 4 there, but originally it was the Kourou Array Telescope. There were 7 of them in the Kourou, and more were going to be built, and so it was called Meerkat, so more Kourou Array Telescopes. Meer is more in Afrikaans, and of course meerkats live in that same region, so it was a clever naming. Astronomers are very good at this. And close to meerkats, the rock dussie or the hyrax also lives in that area, and so because they were going to go on the same site, hyrax was born to live near the meerkats. So, there's some forecasting there for how well we can do in various constraints. And there's also some more images of the dish and some of the people and where the telescopes will go, where the dishes will go. One of the reasons that we could really do this is because quite some time back in 2008 already, 2007, government passed the Astronomy Geographic Advantage Act, which meant that the Kourou has been kept as radio quiet as possible. And so you can see the radio frequency interference in that 400 to 800 megahertz band is extremely low. And that's exactly where you need to observe to get dark energy. So it's perfect for us. And, there's also a whole lot of fast radio bursts in that range. And you can learn more about the experiment at that link. I think it's to me, it's one of the most exciting things happening in cosmology today. So the 8-element array will be at Hartrau, and the main array will be hosted at the SKA site in the Kourou. So we really are partnering with existing projects. And the idea is to put outriggers, so sets of 8 arrays in African countries quite as far as possible from the main array. And some of them are still proposed, it's not necessarily decided, but the idea is that essentially, I'll give you an image for the idea, I think, but essentially it allows you to have a giant dish the size of Africa almost, instead of, many small dishes. So this is the 2 different designs. You can see the one is very light and the other one is far heavier, the white dish on the bottom. And so there was, a process of design going on there. You can see how absolutely beautiful it is. So the place where Hyrax brings a major competitive advantage to fast radio burst science is that if you can localize your bursts, not just to a specific galaxy, but to where they sit in the galaxy, ideally at the edge, as far as I'm concerned, but wherever they are in the galaxy, maybe it will tell you something about the origin of them. We learn what kind of physics mechanisms allow for bursts of that kind, right? You saw already the 4 at the edge gives you a whole lot of questions that you need to answer to. But it'll also allow you to remove off the host galaxy component of the dispersion measure if they're sitting at the edge of the galaxies. So if you can get some, large class of them all at the edges, you can do fantastic cosmology with these bursts. So Hyrax brings about that potential because adding the outriggers allows you to localize them in a spectacular way. I thought I'd put the timeline there and the gorgeous site. I'm not sure how much the timeline will be shifted by COVID, but either way, there's exciting science happening and to be done. And I wanted to sort of finish off with lessons from fast radio bursts that I think are really worth taking away. And they apply outside of just the field of astronomy and cosmology and physics. The one is the way that they were discovered. So FRBs were discovered by changing the way that the data was looked at. They just resolved the data into more frequency channels. And so where a little blip would have been averaged over, if you look at a big bin, by making smaller bins, they could suddenly see that there were these blips. So there was no technological innovation that brought about the understanding that fast radio bursts exist. It was just looking at existing data in a different way. And yes, we need a tech innovation to discover thousands of them. But I think that's a very important thing to realize, is that actually we may just need to change the way we look at some problems to see solutions. We do not necessarily need the revolutions that we think, AI, etc. Let's find some human intelligence perhaps before we go for the artificial one. So I think that's a good lesson. Another lesson is the first one and maybe the first few and maybe the first 100 are not representative. So the first FRB that was really well studied, it's not at all representative. The rest have not followed that pattern. And so, we often do this. The first person you interact with, the people that you interact with a lot, you think everybody's like them, or, you know, your limited experiences, you extrapolate too far from them. And I think we should not do that, right, in science, and we should not do that in society. We should not extrapolate too much from the early data. The next is that with limited resources and limited data, there's going to be bias. There's a lot of bias, not just in the theories that explain fast radio bursts, but also in what we follow up on. So when there's only 3 FRBs, they're studied to death. But when there are thousands, we maybe ignore most of them and study the ones that are easiest to study. So that's something to bear in mind, that there's a bias involved here, and that we have to be careful how we bias what we're doing. Same with what's going on in the world today in many, many spheres. The next point is that we need to keep searching even if we see nothing. I think that may be a hard one for us as scientists, but you don't know what's just around the corner, what's just past the next revolution. And from the astronomy side, we need to look across wavelengths, messengers, and parts of the sky to really understand our universe. And if we cannot set aside our biases, we will find exactly what we're searching for. And finally, through this pandemic, people talked about 5G. If you want to worry about 5G, you should worry about the RFI that it contributes that ruins our experiments. But I think there's great potential for discovery. There are a lot of new puzzles and new ideas out there. We don't always have to be working on the hardest problems. Sometimes like small, interesting puzzles lead to great insights about our universe. And finally, I just wanted to thank you again for allowing me to take my head outside of the everyday. I mentioned to Francesco, but my aunt, Marcia of blessed memory, passed away this weekend. And it's been a difficult time. It's been a difficult year for many of us. And just having a chance to focus on, take your head out of the earth and into the clouds has been a privilege. And, you know, I thought the quote of Alexander Graham Bell is very apt here, that we should concentrate our thoughts upon the work at hand, because the sun's rays do not burn until brought to focus. So as difficult as it can sometimes be to pop our heads out into the sky, it's a privilege. So thank you for giving me this chance.
Amanda, thank you very much for an excellent talk and for sharing with us a fantastic overview of cosmology, of radio astronomy, and bringing us up to speed with the latest in observation and theories. So thank you very much, in particular during a personally challenging time. At the beginning of Amanda's talk, Professor Kavilan Mudli joined us, and I had asked him to kindly help us moderate the questions that the participant might want to ask to Amanda. Kavilan, thank you for joining us, and I see that we have one question, but I'm sure that while you process the first question, many more will pop up. So please don't be shy and ask questions using the Q&A facility. We still have some time. Kavilan, can I ask you please to moderate the question session?
Yeah, thanks, Francesco, and yeah, thanks, Amanda, for an excellent talk. And I guess my condolences on your loss. It's difficult times you're going through. There's a one question, but I'd like to encourage the audience to put more questions down. So the first question comes from William Horowitz, and he really enjoyed your talk. He asks about, you mentioned one possibility for understanding data is a modification of gravity. So he asks you, if you had to bet on the type of modification, do you think it would be some slight modification to Einstein GR, for example, to a correction to the Einstein-Hilbert action, or something more dramatic in the axioms of GR, for example, you know, on the order of transitioning from Newtonian to Einsteinian gravity? And if it's the latter, where might one look for the modification?
It's a hard question. So I'm not a betting person, so I probably wouldn't bet on this. But I don't know. You know, I think that there's a good chance that general relativity is fully correct, and that it's just that we do not fully understand the realm. We don't fully understand the realm in which it no longer is valid, which is beyond quantum field theory. And so I don't know where that right answer, what the right approach would necessarily be. If I did, I would be working on it, right? I think that we've only done the very easy things, that's for sure, right? And the easy things are add particles, add simple scalars. But if you wanted to look for modifications, I think you'd have to figure out what you're willing to let go of: locality, unitarity. Yeah, I think you'd have to decide which of the axioms you feel are sacred. To me, they all are still. So I find it very hard to look at true modifications of GR, not of gravity, right? Because gravity is gravity. It's GR that we wonder if it needs to be modified or not.
Okay, thanks very much, Amanda. So I'll just mark that question as answered. The second question on the Q&A. So yeah, if you would, you can either use the Q&A or the chat. I'll take both places. So the second question on the Q&A is from Azundini Muronga. He says, thanks for an excellent talk. How will the SKA answer some of the dark matter and dark energy questions?
So SKA will do a lot more than HIREX in the sense that it looks at different timescales as well. So it will go. It's both broad and deep as a survey, right? So in similar ways to other cosmology surveys, we should be able to get constraints on different types of dark matter, the way that dark matter and dark energy each contribute to the parameter space of cosmology. What I think it won't do is tell you anything about the nature of dark matter or dark energy. I think there's no direct, I mean, I could stand corrected. Actually, that may not be true. There may be predictions of a particle nature of dark matter that the SKA could also constrain. I'm not sure. Yeah.
All right, thanks, Amanda. So I guess I'll skip to the dark matter question.
While we're on the topic.
While we're on the topic, and that's from Paul Fallon, and he asks, in terms of dark matter, what is the latest thinking in terms of a more likely cause, either between modified gravity or new particles?
So I think with dark matter, most of the thinking is new particles. I don't think there's as much sort of the modified gravity community is smaller and maybe less heard. So I think the thinking there is that it's a new particle, and I think personally the most compelling case is the ultralight dark matter, sort of ultralight axion type particles. It make a very compelling case, and that's sort of the work of Lamhui, Ed Witten. It was a group of them, but there's a bunch of work in that direction. So I think the new particle idea is the most compelling there. And it's just figuring out what the properties are and how do we possibly do non-cosmological observations, because the observations that tell us that dark matter exists are, they're now priors. We need to do observations that that don't already use those assumptions. So yeah, direct detection would be fantastic, but I don't know if it's possible. There are a whole lot of incredible small lab experiments that have been built to search for dark matter particles, Abracadabra and ADMX. There's a whole bunch of them all over, but they've found nothing so far. So they're really clever experiments, and I admire all of them, but so far nothing. But my thinking is that it will still eventually be a particle. Yeah.
Okay, thanks, Amanda.
Modified theory, yeah.
Thanks very much. So there's another question from Isabel Kolb from the University of Washington, and she thanks you for a great talk. So she asks, why can't one do this business with the way that the frequencies of the FRBs are separated by the intergalactic baryons with any extragalactic source that produces pulsars in at least two different frequencies? For example, why doesn't a pulsar work?
I'm not sure what the question is. Why doesn't a pulsar work?
Why? So in terms of getting, I guess, the dispersion measure, etc. Why?
Oh, it's the radio. It's because it's in the radio. Yeah. So if there's radio emissions from a pulsar, then they would also interact and be slowed down in that same. You're asking about the 1 over nu squared behavior, right? That's what she's asking.
Yes, yeah. So yeah, why doesn't it happen in any extragalactic source that produces?
I think it's because of the frequency. So I think that the frequency in the radio they interact with that, with the electrons along the line of sight. And so they are slowed down. I think if you have if you imagine a much higher energy photon, they pass through without that interaction. Then they don't interact with the intergalactic medium in the same way.
Yeah, I guess just to add also the strength of these fast radio bursts. I mean, they're very bright, so they can be seen at cosmological distances, whereas pulsars are much fainter, for example. So it would be harder to detect them. Yeah.
Yeah, you're not seeing them as far out. That's right. Yeah.
Yeah. Okay, so there's another question on the Q&A from Ismail Al-Kawalia. So he says, it's an awesome talk. Could you please explain a bit more about how the CMB hotspot sizes constrain the geometry of the universe, and is that sensitive?
So I think it's only one measure. So you wouldn't bank on that. You need other measures as well that give you the geometry. But essentially, because if the curvature is very, very small, you need to look over very long distances to see its effects. And so the CMB is very good for that. And so just to explain again, maybe I explained it too quickly. Essentially, if you imagine, if you're moving in a flat universe, then the light is moving on straight lines. If you're moving in a curved universe, then what you think is a straight line is actually a curve like that. And so if I were to map back the photon that I see here, if I were to map it back to the earlier universe, it would come from a different spot size. And if you're moving in an open universe, the angle is also different. So you get different characteristic sizes. And that's sort of why it works. But it's not the only measure. We have to put together all the data, and the data all together tell us that the combination of mostly flat, with dark energy seems to work. If you add dark energy in at the very end of that picture, you can imagine that you confuse yourself. And so if the universe is expanding in an accelerated way at the very end, this guy suddenly accelerates out. So how could you tell the difference? And that's why it's important to figure out the difference between dark energy and curvature.
All right, thanks so much, Amanda. I think that's it in terms of the questions on the chat or the Q&A, and I guess we've gone past the hour, so I'm going to hand it back to Francesco. Maybe to close
thank
up.
you very much, Kevin, for mastering the question session. Thank you very much. And again, Amanda, thank you so much for a really fantastic talk. And you saw from the feedback from the participants that there is lots of interest. And I hope that soon you will be back in the NITheP Colloquium for updates on more recent developments. So thank you very much to all the participants. And I hope to see you soon at the next NITheP webinar. So thank you very much again, Amanda. And thank you, Kabilan, and thank you, Ilya, for the technical support. Yeah, thank you very much. Have a good evening all together.
Thank you.
Bye.
Thank you.
Thank you. Bye-bye.